Okay, so this video is to explain in another way the typical inclined plane problem that we had and that some of us were having trouble with. If you'd like to watch this to study for the quiz this week, the problem will be very similar on that, so it'll definitely be worth your time. Okay, so you can see here's the problem that we had on the test. So on the test, we had a problem and it said, consider a box being pushed from rest 3 meters up a slope. So it's being pushed over this distance right here. 3 meters, the force that's pushing it is 150 newtons. That's pretty big if you consider like the typical weight of a person in kilograms times g. So that's a pretty big pushing force. You might imagine there's an elephant down there pushing it up the hill or something. I don't know. But it's being pushed up the hill for 3 meters. The box has 20 kilograms, so it's a pretty heavy box. And the coefficient of kinetic friction we're given is 0.25, and the slope has a constant angle of 30 degrees throughout that 3-meter journey. Okay, so the first question that we need to be able to do is how much work is done by gravity, and then we'll look at how much work is done by friction. So first of all, as we talked about in class, it's good to draw a free body diagram. So we'll think of like this point in the center of the box as where we're going to show our vectors. So gravity is obviously coming down in a perfectly vertical fashion. So there's gravity, but gravity can be thought of as a couple different vectors. So let me get a different color. Let's do green. So you can think of gravity as the sum of the action of these two vectors. So you've got these two vectors. So instead of just thinking about that, since you're on the plane, you can think of these two vectors adding up to the force of gravity. So gravity, like we had before, was mg, of course, so we all know that. We're going to say this angle in here is theta, okay? Get rid of some of this other stuff. And now we're basically going to figure out these two things. So let's just call this one A and this one B, and we'll worry about what they are in a second. So if we take the cosine of theta, then we get adjacent over hypotenuse is A over mg. So mg cosine theta, in other words, is equal to A. So the question is, what is A? Well, A is the same thing as the normal force. You can see that it's perpendicular to the surface. Here's the normal force. So A is just the same thing as the normal force, Fn. So now you have the normal force. Okay, so that's a pretty valuable thing to have if you want to know friction. So you say, hey, they asked how much work is done by friction, so that's just the 3 meters that it was pushed times mu k times, what's this guy? This guy's Fn, right? Because the force of friction, you have this little relationship that says it's the coefficient of friction, whatever type you have, static or kinetic, times the normal force, and we just found the normal force. So we've got that, so there you go. You want to make sure your calculator is obviously in degree mode, especially if you're in calculus. Okay? Alright, so let's see what else we have. So I'll change colors. We'll say this guy is B. So we'll do B. So B is involved with the sine of theta. So I'm going to take the sine of theta, and that way I'll get B in there. Uh-oh, running out of drawing surface. So there we go. So in other words, mg, try to write small, sine theta is B. So the only question is, what is B? And yesterday we talked about how when you're thinking about gravity, gravity is pushing straight down, but when you're on a slope, it's not really pushing straight down anymore. It's kind of pushing in this kind of fashion, right? That's kind of what's happening due to gravity. So in other words, B is the component of gravity along the slope. So that's what we're going to think of here is we're going to call this gravity. So let's call it gravity down the slope. So gravity subslope or something like that. However you want to call it, that's equal to mg sine theta. So when you're doing the work done by gravity, you can see there's your gravity down the slope times 3. That's the distance. So there you got that. And both of those were negative, right? They're both going against against that pushing force. So we're going to remember that we defined this as up. Going up the slope is positive. So those are both negative works. Like we talked about earlier for number 17 here, how much work is done by the normal force? The normal force is always perpendicular throughout this little trip here. So any force that's perpendicular doesn't do any work, so there's no work there. How much work is done by the pushing force? That's another easy one. It's just the force, it's always parallel to it, so it's always going to use all that 150 newtons, and it goes for 3. When it gets pushed, it's traversing this little distance of 3 meters, so 450 joules there, and that's positive. So the most important question we had was how fast is the box moving? And this is something you have to get right on the quiz, or you're not going to get any credit. It's just a big important thing. So we need to know the work energy principle applies here. So how do you convert between work and energy? Well, remember the total amount of work is equal to the change in kinetic energy over a trip between 2 points in a system. So our total amount of work here is going to be what? I guess I better make some more space. So our total amount of work is going to be 450. We don't have to worry about the 0, but minus 294 minus 127.5, and that's going to be equal to change in kinetic energy. So kinetic energy final, kinetic energy initial. And kinetic energy has that velocity squared term, right? But the block started from rest, so the initial is going to be 0. So then we're going to have 1/2 mv final squared equals that number. So that number turned out to be, let's see, 28.5, I think. So we got 28.5 positive joules of work. And then we just multiply that by 2, so I'll do it over here. So we go 28.5 times 2 to get rid of that half, divided by where's my m? I don't know where my m went on here. Maybe I have the wrong answer. So we should have that times 2. Yeah, I don't know. So let's see. Square root of 28.5 times 2. And that should be divided by our mass. So what was our mass? 20 kilograms. So divided by the mass. And square rooted. So that's going to be equal to, if I put it in my calculator, 1.689 meters per second. And if we did significant figures here, I guess we can keep a lot of those because we have all of these worked out to 3 significant figures, so it could be 1.69, but we're not going to worry about that too much. Okay, so I hope you found this useful.